During this week, you will finish any IR analysis of VOacac2 if you were not able to complete it last week. You will then dissolve VOacac2 in several solvents and take the UV-Vis spectrum of each solution to determine any difference in Lewis-base interaction between the solvents and VOacac2. Finally, if asked by your TA, you will provide a small sample of product to them so they can complete magnetic susceptibility measurements on this compound. The resulting measurements will be provided to everyone in your group and then can be used to determine the number of unpaired electrons in VOacac. The structure of the 5-coordinate vanadilyl bisacac complex is square pyramidal, with vanadium displaced slightly above the plane of the 4 oxygen atoms attached to the acac ligands. There are 2 different vanadium-oxygen bonds that are present. The single axial-vanadium-oxygen bond is shorter and has a length of 1.59 angstrom and can be considered to have multiple bond character. The 4 dative bonds between vanadium and the oxygen atoms in the acac ligands are longer, and each has a length of 1.97 angstrom. This week's lab attempts to coordinate several solvent molecules, or Lewis bases, to vanadilyl bisacac, forming a 6-coordinate complex. Pyridine, dioxane, and tetrahydrofuran are Lewis bases, since each has at least 1 electron pair that can be donated to a Lewis acid. The presence of a lone electron pair allows them to form a dative bond with vanadium and vanadilyl bisacac, converting it from a 5-coordinate to a 6-coordinate complex. The addition of a ligand such as pyridine in the 6th coordinating position affects the IR stretch of the VO axial bond as well as the UV-Vis spectrum of this complex. Both spectra can provide evidence that a monodentate ligand has formed a dative bond in the 6th position of the complex. The d orbitals of a transition metal are degenerate in the absence of any attached ligands. Since each orbital can hold a maximum of 2 electrons, the d sublevel has a capacity of 10 electrons. Each d orbital has a definite orientation in space, and the presence of ligands bonded to the transition metal affects the energies of these orbitals. This effect is apparent in the visible spectrum of transition metals, since most exhibit a characteristic color when bonded ligands are present. This schematic shows the relative energies of the d orbitals in a transition metal for some specific structures. The d orbitals in an isolated transition metal atom or ion all have the same energy. In this case, they are called degenerate. When 4 monodentate ligands bond to the transition metal in a tetrahedral arrangement, all 5 orbitals are elevated in energy and then split into 2 sets, one slightly lower in energy than the other. If 6 monodentate ligands bond to the transition metal in an octahedral arrangement, the orbitals are also elevated in energy, split into 2 sets, but the order is reversed relative to a tetrahedral environment. A square pyramidal arrangement of 5 atoms bonded to the transition metal is a variation of the octahedral arrangement, with the orbitals split into 4 groups. The d electrons in a transition metal complex can be excited from a lower to a higher orbital by absorbing visible light. The color we see is the complement to the color that's actually absorbed. For example, a transition metal complex that absorbs yellow light will appear blue. One that absorbs violet will appear green, and so forth. The spectrum produced by a UV-Vis spectrometer records the wavelength that's absorbed. The vanadilyl bisacac complex is square pyramidal, allowing a basic ligand to bond at the 6th position. The addition of this 6th ligand affects the original energy of separation of the d orbitals in the square pyramidal complex. The energy separation is represented by Roman numeral 1 in the schematic above, and is more affected than the energy of separation 2. This effect can be shown by comparing the visible spectra of the 5-coordinate and 6-coordinate complexes. The effect of attaching a basic ligand to vanadilyl bisacac can be shown in both the IR and UV-Vis. The addition of any Lewis base to the 6th position decreases the strength of the axial vanadium-oxygen bond, and the IR frequency of this bond is lowered. Strong base ligands can shift this stretch by 50 reciprocal centimeters, medium base ligands by 25 reciprocal centimeters, with weak base ligands showing little or no shift. There are two broad absorbances in the visible spectrum, and there is a slight visible color change when a base forms a dative bond in the 6th position of the vanadium complex. This is because the visible light energy required to excite an electron from the dxy orbital to either the degenerate dxz and dyz orbitals, or to the higher dx squared minus y squared orbital, is affected. The effect of the base ligand on these two transitions can be shown by a shift in the respective lambda max of the visible spectrum for both of these absorbances. The visible spectrum of the vanadial bis acac shows the wavelength of light absorbed when a d electron is excited to one of two higher energy levels. Since there is an inverse relationship between wavelength and energy, a lower lambda max, such as the one at 598 nanometer, is higher in energy than a high lambda max, such as the one at 680 nanometer. The lower lambda max represents the excitation of a d electron to the dx squared minus y squared orbital, and the higher lambda max the excitation to the lower and degenerate dxz dyz orbitals. As the strength of the Lewis base is increased, the 680 nanometer absorbance shifts to higher wavelength. That is, the energy required to excite the electron to the degenerate dxz dyz orbitals decreases, and the 598 nanometer absorbance shifts to lower wavelengths, or more energy is required to excite the electron to the dx squared minus y squared orbital. By recording the lambda max for both transitions for a set of solvents, a series could be devised based on the difference between the two lambda max, listing the solvents in order of increasing base strength. We can summarize the effect of increasing base strength of a ligand attached opposite the axial vanadium-oxygen bond. As base strength increases, the wavelength of the lower d orbital transition increases, indicating a decrease in absorbed energy, and the wavelength of the higher d orbital transition decreases, meaning an increase in absorbed energy. The IR frequency of this vanadium-oxygen bond decreases with increase in Lewis base strength, indicating that the bond strength decreases. Now, a new property called magnetic susceptibility will be measured for the vanadial bis acac. Magnetic susceptibility is useful in determining how a substance interacts with an applied magnetic field and provides insight into the electronic structure of the compound. Substances are typically categorized as either diamagnetic or paramagnetic. Diamagnetic substances oppose an applied magnetic field as a result of having no unpaired electrons. Paramagnetic substances, on the other hand, are attracted to an applied magnetic field because they have unpaired electrons. This effect of diamagnetism or paramagnetism is measured using a special balance. A GUI balance is essentially an analytical balance with a strong magnet located beneath the balance pan. When a given sample of a substance is placed on the balance pan in the absence of a magnetic field, a normal weight is measured of the sample. The presence of a magnetic field beneath the balance pan, however, can affect the measured weight. If a substance is diamagnetic, it is repelled by the magnetic field, and its apparent weight is less than its actual weight. If the substance is paramagnetic, it is attracted by the field, and it weighs more than it would with no magnetic field present. The absolute value of the change in weight for paramagnetic substances is greater than this change for diamagnetic substances. The GUI balance was useful in explaining the effect of magnetic fields on the apparent weight of diamagnetic and paramagnetic substances. We will be using a more modern instrument called the magnetic susceptibility balance. The fundamental parameter that this balance measures is R. R is near zero or negative for diamagnetic substances, whereas it is positive for paramagnetic substances. The absolute value of R for paramagnetic substances is larger than the corresponding value for diamagnetic substances. The MSB works differently from the GUI balance, with the sample remaining stationary, with this balance attempting to counter the sample's magnetism. The magnetic susceptibility Chi subscript G varies directly with the measured length of the sample, two readings from the magnetic susceptibility balance, and inversely with the mass of the sample. The magnetic susceptibility is converted to molar susceptibility, Chi subscript M, by using the formula weight of 265.16 vanadiol bis acac. Diamagnetic corrections are subtracted using tabular values to give Chi subscript A. Chi subscript A is then used to determine mu effective, which then can be converted using a table to give the number of unpaired electrons in vanadiol bis acac. This calculation is not difficult but can be tedious. You will probably want to calculate mu effective shortly after obtaining your R reading of vanadiol bis acac from the magnetic susceptibility balance. Using data provided by your TA and tables in the lab manual, you can determine the number of unpaired electrons in VO bis acac. Your UV-Vis data for VO bis acac dissolved in several solvents will allow you to construct a series for these solvents ordered by base strength when coordinating in the 6th position of VO bis acac. Additional instructions for the lab write-up are provided in the lab manual.